Okay, so today I have a guest with me. His name is Yobs.
Hey, how you
Yobs,
guys doing?
introduce yourself.
Hey, how you
So,
guys doing?
how's it going, bro? So, Yobs, can I ask you a question? What is, uh, can you define what is an eigenfunction?
So you could think of an example. So
You
you
gotta speak
have
louder because you're speaking.
yeah. So you can think of an example, and one of them is the derivative system, and let's say you have an input x squared, and the output here would be 2x, right? And if you had another input, let's say you have x cubed, you'd have 3x squared. Um, this
Uh,
so this is an example of
this is an operator. The
yeah
derivative is an operator,
yeah
and so and this is just an input.
hmm
You can think of it as a function, but it's not really a function.
yeah. So
So
the
it's like I apply a function. Well, it is a function. X squared is a function. So I apply a function onto an operator, and I get a corresponding output.
yeah. So this is your output. This guy's your operator.
So, Jobs, what happens if I pass a complex number on or any function of e onto the derivative operator?
Yeah. So if we had an example like this, we would have the output of that. So you can see that this is some constant, which happens to be the correct me here, the eigenvalue.
The eigenvalue.
Yeah, the eigenvalue, and this is the what is this again?
This is the eigenfunction.
Yeah, and this is the
And
eigenfunction.
why is it the eigenfunction? It's the eigenfunction because the input to the operator, I pass a function into the input as an operator, and the corresponding output is a constant times that function.
Yeah.
Which
So
means if I pass in an input, a function onto an operator, and I get the corresponding function multiplied by a constant, that means that function must be a eigen function to the operator.
yeah, so you could represent it as input function. You'll have it on the output side times some constant. Right. All right. So I'll let Aziz take over here and explain. We're trying to prove um, problem 8 from our homework 4.
Do you have it up? So, you, is this even recording?
Yes.
Okay. So, it says that if I have an input x of t, and I pass it on to subsystems, namely h1 and h2, and I get a corresponding output y. And it's given that both h1 and h2 are LTI systems. Given that both h1 and h2 are LTI systems, for any LTI systems, and you can derive this on your own if you want, using the definition that I've given. For any LTI system, if the input is a sum of e to the I j omega t's, then the corresponding, and given that, and what I'm proposing is that this e to the I j omega t is an eigen function
Mm-hmm.
to any LTI system.
Yeah, that makes sense.
So, as we have derived before, and this will be a second derivation actually. Okay, this is kind of like a divergence for a bit, but it's a short divergence actually. Given that I have my input is a complex exponential, and if I pass the input onto an LTI system, that means the corresponding output must be a complex exponential times some constant. And this is basically the gist of what a transfer function is. So, knowing that if I pass an input that if I pass an input x of t onto an LTI system, that the output I get is just equal to the input convoluted with the output as I have derived previously. Then
with the output,
with the impulse response.
impulse response. Yeah.
Thanks for correcting me. So it's just equal to that convoluted with the impulse response. That means that if the input is e to the I j omega t, then the output is just equal to the integral. This is just a definition of what a convolution is. Given that my input is e to the I j omega t, that means e to the I, no. Why do I have two i's?
Yeah.
My bad. Okay, I'm getting confused. E to the j omega t, where in this case t shifted by tau, because this is just a definition of what a convolution is, times h of tau d tau. What we notice is that if the output is equal to this, I can separate the time, what depends on the integration variable, which is a dummy variable that I'm integrating over, versus the constant. So in this case, I can separate e to the I omega t out of the integral because it's constant with respect to the dummy variable, times e to the j minus j omega tau h of tau d tau. So what I have proven is that I can separate the time dependence of the output with what you can refer to as a constant with respect to time, or also with respect to the system. And this is namely equal to the transfer function, which is written in terms of j omega. Given that I have this information, and since j omega clearly does not depend on time, it's just a constant with respect to the output y of t, and the only time dependence comes from this term. So given that I know that if the input is a complex exponential, namely a sum of complex exponentials or whatnot, if I pass this onto an LTI system, knowing that the output of the LTI system is just equal to j omega t times the transfer function j omega, given that I know that, and since this system here is just the operator that I've shown before with the derivative operator, that means that this complex exponential is an eigenfunction of the LTI system, because the corresponding output is just some constant that's independent of t times the eigenfunction that I passed into my LTI system. So if I have two cascading inputs, then given that this is the output of the first system, h1, the output of the second system, h2.
I see. Okay, it's clicking now, just to let you know.
The output of the system h2 must be equal to e to the j omega t plus the previous constant, which I'll define as h j omega. Since a constant times a constant is always a constant, it doesn't really matter. That means it'll just be equal to the eigenfunction times
the new constant,
which is the new constant I get by passing it into the second system.
Yeah, h of 2, right? Yeah.
H of 2.
Yeah.
I can, if I really want to, for some reason, I don't know why I would do that, I can write this as, this is equal to the h j omega of the h total, which I define to be equal to the passing in the input onto the cascading system.
Yeah.
Does that make sense?
Yeah.
So my friend Yabs will wrap up this video.
Yeah. So he has shown that h of the total h is equal to the two transfer functions. All right. Thanks, guys, for watching. See you soon.